Hello and welcome to the Material Podcast, the show that we explore the breakthrough shaping the world. I am your host, Natapon Kongsip, or you can call me Omsin. And today we are driving into the ultra thin but enormous potential. You might have heard about graphene, right? Or seen headline about super thin flexible screen or even quantum computer. At the heart of many of these future technologies is a fascinating class of material known as 2D materials. Materials so thin they are only single atom thick, they are not science fiction, they are science fact. But how did this all begin? Why are scientists around the world so excited about material you can't even see with the naked eye? And what could these tiny layers mean for our life in the next 20, 30 or even 50 years? To help answer these questions, I'm joined to two researchers in this field. First, we have Dr. Bell, a physicist who study the origins and quantum properties of 2D materials, include the legendary story of how graphene was first discovered. Welcome, Dr. Bell.
Thank you, Omsin, and I'm happy to be here.
And with us as well is Dr. Room, a material scientist working on cutting-edge applications for wearable tech to AI chips, or powered by the magics of atomically thin materials. Welcome, Dr. Room.
Thanks, Omsin. It's great to be here.
So let's get started with a question that take us all the way back. What are 2D materials and how did scientists first manage to isolate something so thin? It almost defies logic.
Good question, Omsin. So let's take a short journey through history. For most of history of science, material were thought of as three-dimensional, right? Height, width, and depth. You can make things smaller, thinner, but the idea of something being just one atom thick, that sounds like fantastic or the best theoretical. In fact, for many years, physicists believed 2D crystals couldn't exist in nature. The theory said they be too unstable, they crumble due to thermal vibration or defects. So for decades, the idea of 2D material was kind of left on the shelf. Then everything changed in 2004 at University of Manchester. Two physicists Andrei Game and Novoselov did something almost too simple to believe. They used regular Scotch tape to peel the layer of a piece of graphite. They kept sticking, peeling, folding until eventually they isolated a single atomic layer of carbon atom and arranged in a perfect honeycomb structure. There was a graphene, and this is our first true 2D material ever created. It sounds funny, right? They call it the Scotch tape method, but it was so low-tech, but it worked. And this material, it had excellent properties, including 200 times stronger than steel, incredibly flexible, nearly transparent, and one of the best electrical and thermal conductor we ever seen. And the world took notice. In 2010, James and Novoselov were awarded the Nobel Prize in Physics, not just for discovering graphene, but for opening up the entirely new branch of material science. And suddenly the question wasn't, is this real? It became, what else is possible? Could we find other material, 2D materials? Could we stack them? Could we build new devices from atomic level upward? And that's exactly what scientists began doing next, leading to what many call the 2D material revolution. So what started with a piece of tape led us into an entire new world of possibility, and that was just the beginning.
Amazing! From something as simple as tape to a Nobel Prize and a whole new field of science. So, Room, what came after graphene? What other 2D materials have joined the family?
Great question, Omsin. Graphene was just the first domino to fall. Once we saw how powerful graphene was, the scientists asked that, are there other materials that can exist in 2 dimensions? And the answer is yes, dozens of them. Some of the most exciting include molybdenum disulfide. It's a semiconductor unlike graphene, which doesn't have a band gap. That makes molybdenum disulfide great for transistors and photodetectors. Next is a hexagonal boron nitride. It's an excellent insulator, often called white graphene. It's used to protect or separate layers in 2D stacks. Next is a tungsten diselenide. It's a black phosphorus or MCs, and many more. Each with unique properties for electronics, optics, and energy. But here where it gets very cool. We can stack these 2D layers like Lego block one atom layer at a time. Because these structures van der Waals historical structures. By combining a material with different properties, maybe a conductor and insulator, and a semiconductor, we can engineer entire new materials that doesn't exist in nature. This stacking unlocks new physics like tunable band gaps, strong excitonic effect, and even exotic phenomena like Moore superlattices, which can show superconductivity or other quantum behavior. So, graphene may have started the story, but the 2D material family has approached into diverse toolbox for building future devices, atom by atom.
That's incredible. It's like making your own design materials for any purpose you want. So we've got a lot of new materials and we can build with them. But what is standing in the way of real world use?
Yes, this is where reality hits a bit harder. The biggest challenge today is scalability. It's still very difficult for a grow or synthesize large area of 2D materials with perfect quality, no cracks, wrinkles, or defects.
Especially when you're dealing with materials only one atom thick. Even tiny contaminants or air exposure can ruin them. Can transferring them onto chip or devices without damage? That's another tricky step.
But we are making progress. Today we already see 2D material in flexible electronic like foldable screens, transparent conductive film in touch display, photodetectors and solar cells that are ultra light and fast, and water filtration membranes that filter molecules with atomic precision. There are even sensors so thin and sensitive they can detect a single gas molecule, perfect for environmental monitoring or health diagnostic.
So even with the challenge, we are already seeing these materials enter the real world?
Exactly. The lab to market part is slower than the hype, but it's happening one atom at a time.
Let's look ahead. If you could fast forward to 10 or 20 years, what future do you see for 2D materials?
For me, it's about discovery. We only scratch the surface. There could be hundreds or thousands of 2D material waiting to be synthesized. Some may have unusual quantum behavior such as superconductivity, magnetism, or topological properties. The idea that we might one day design quantum computers or quantum networks using stacked 2D materials. That excites me.
And on the application side, I dream of a world where we add 2D sensors into our clothing or skin, giving us a real-time health tracking like blood oxygen, hydration, glucose without a bulky device. Also, imagine AI chips made from 2D semiconductors, super fast and energy efficient, helping reduce the carbon footprint of cloud computing and data centers. 2D materials could also revolutionize space tech because they are incredibly light and radiation resistant. We might build satellite electronics with layers thinner than a sheet of paper.
That's inspiring. That's amazing how something so tiny could shape so much of our future. Thank you, Dr. Bill and Dr. Rung, for that fascinating journey from peeling graphite with tape to quantum tech and wearable health sensors. And to our viewers, we hope today's story shows you that even the thinnest materials can lead to the biggest breakthroughs. Until the next episode on the Material Podcast, stay curious and keep exploring. See ya!